When people first hear the phrase secure architecture, they sometimes imagine it means buying a bunch of security products and plugging them in like extra locks on a door. In operational technology, OT, architecture is less about gadgets and more about how the environment is designed to behave under stress, including mistakes, failures, and attacks. A secure OT architecture tries to make bad outcomes harder to reach, even when something goes wrong, by shaping pathways, permissions, and visibility in a deliberate way. For brand new learners, the challenge is that OT is not built like typical office IT networks. It is often purpose-driven, time-sensitive, and designed to be stable for long periods. That stability can help security because normal is predictable, but it can also create risk because old assumptions linger and changes are harder to make quickly. In this lesson, we will anchor on 3 architectural principles that appear again and again in good OT security conversations: least privilege, determinism, and defense in depth. These are not slogans meant to sound smart. They are practical ideas that guide how you limit damage and keep operations safe. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Least privilege is the principle that people, devices, and software should have only the access they need to do their job and nothing more. Beginners sometimes think least privilege is mostly about employees and passwords, but in OT it goes wider because access can mean the ability to change logic, push firmware, adjust set points, or even just reach sensitive segments. The reason least privilege matters is simple. If an attacker compromises an account or a system, the damage they can do is limited by what that compromised thing is allowed to do. If every administrator can reach every controller network, then one stolen credential becomes a master key. If a vendor remote access account can access a jump host but cannot directly reach safety-related engineering workstations, then compromise of that vendor account is less catastrophic. Least privilege also reduces accidents, because human mistakes are real, and an accidental change made with excessive permissions can break a process just as surely as a malicious change. In OT, where safety and uptime matter, limiting permissions is a form of risk containment that helps both security and reliability. To understand least privilege in an OT context, it helps to think in layers of capability rather than in job titles. Some roles need read-only visibility, like viewing dashboards or trends, and they should not have write access to controllers. Some roles need the ability to acknowledge alarms and respond operationally, but not to change controller logic. Some roles, like control engineers, may need to make changes, but even then their access should be scoped to specific systems, specific projects, and often specific time windows. Devices also have roles. A historian server might need to read process data, but should not need to write control commands. A patch management system might need to distribute updates in the enterprise, but should have tightly controlled reach into OT supporting servers. Least privilege can also include the concept of separation of duties, meaning no single person or account should be able to perform a high-risk action from start to finish without oversight. For beginners, the key insight is that least privilege is a design habit. You define what must be possible, and then you eliminate everything else. That elimination shrinks the attacker's options and reduces the chance of accidental harm. Determinism is a principle that is especially important in OT and less common in everyday IT conversations, and it refers to predictable, repeatable behavior that supports control and safety. Many industrial processes depend on systems responding within specific timing and performance expectations, and that means the network and the devices are often engineered to behave consistently. Determinism in this sense is about knowing what should happen and when, so that the process stays stable and safe. From a security perspective, determinism is valuable because it makes anomalies easier to detect. If traffic patterns, command sequences, and system behaviors are usually consistent, then unexpected behavior stands out. However, determinism also creates challenges, because some security practices that are normal in enterprise IT, like frequent scanning or heavy endpoint agents, can disrupt timing-sensitive systems. That is why OT security often emphasizes passive monitoring and carefully planned changes. For beginners, determinism is a reminder that OT systems are not just computers. They are parts of a control loop, and the timing of that loop matters. Security architecture must respect that reality, or it can create risk on its own. Determinism also influences how you think about change, because an OT environment that is deterministic tends to be change-averse for good reasons. If a system controls a critical process, you want it to behave the same way today as it did yesterday unless a change was deliberately made and validated. That mindset supports strong change control and baseline thinking, which are helpful for security. It also means you can treat unexpected changes as high-signal events. For example, a new communication path between zones might be more suspicious in an OT network than in an office network, because OT networks typically do not have constant churn. Similarly, an unexpected reboot of an engineering workstation during a quiet period might deserve attention because it breaks the expected rhythm of operations. Determinism helps you ask the right questions. Is this behavior consistent with the process requirements, the maintenance schedule, and the approved changes? If not, why is it happening? When you design architecture with determinism in mind, you build visibility into what normal looks like, and that makes it harder for attackers to hide in randomness. The principle is not that everything must be static forever, but that change should be intentional and observable. Defense in depth is the principle that you do not rely on a single control to protect something important, because single controls fail. In a simple analogy, you do not trust one lock on the front door if the stakes are high. You also have a deadbolt, lighting, a way to see who is outside, and perhaps a fence. In OT, defense in depth is essential because environments are complex, equipment life cycles are long, and some vulnerabilities cannot be patched quickly. If you assume any single layer will hold forever, you will eventually be disappointed. Defense in depth means you combine multiple layers that address different parts of the problem, preventing access, limiting movement, detecting abnormal behavior, and enabling safe recovery. It also means placing controls where they reduce risk without breaking operations, which is a balancing act. Beginners sometimes treat defense in depth as more stuff, but the better interpretation is more opportunities to stop or limit harm. If one layer fails, another layer slows the attacker or contains the blast radius. That layered design is what makes architecture resilient. In OT, a defense in-depth mindset often shows up as thoughtful segmentation and controlled conduits between zones. You separate business networks from operational networks, and within operational networks, you separate different levels of criticality and function so that compromise of one area does not automatically grant access to everything else. You also use access controls at multiple points, such as authentication at remote access entry, authorization at jump hosts, and scope permissions at engineering tools. Monitoring is another layer. Even if an attacker gets in, you want visibility into unusual sessions, unusual traffic flows, and unusual changes. Backup and recovery is a layer too, because it supports restoring trust after an incident. Physical security can be another layer, because in many OT environments, physical access can create cyber access through cabinets, ports, and removable media. The most important beginner lesson is that defense in depth is an architectural approach, not a product list. You choose layers that complement each other, and you place them in the environment so that each layer has a clear purpose and does not create unsafe operational friction. These three principles also reinforce each other in practical ways, and seeing those relationships helps beginners avoid treating them as separate chapters. Least privilege limits what an attacker can do if they gain access, which strengthens defense in depth by reducing the consequences of a breach at one layer. Determinism makes it easier to notice when something is off, which strengthens defense in depth by improving detection and creating clear baselines for investigation. Defense in depth supports determinism by reducing the chance that a single failure or compromise will cause chaotic behavior, because layers can prevent or absorb changes. In a well-designed OT architecture, you might see least privilege implemented through narrow access roles, determinism supported through stable configurations and clear change control, and defense in depth expressed through segmentation, monitoring, and recovery planning. These ideas are not theoretical. They show up in everyday decisions like where remote access lands, who can push controller changes, and how traffic is allowed between segments. When beginners learn to connect the principles, they start to evaluate designs more effectively. Instead of asking whether something is secure, they ask how it limits harm, how it stays predictable, and what happens when a layer fails. A common misconception is that these principles make systems harder to use and therefore impossible to adopt in real operations. In reality, the best architectures try to create secure convenience, meaning the safe way of doing work is also the easiest and most supported way. If least privilege is implemented in a way that constantly blocks legitimate tasks, people will find workarounds, and workarounds create shadow pathways that are often less secure. If determinism is enforced without flexibility for real maintenance needs, operations will be forced to improvise changes under pressure, which increases risk. If defense in depth is treated as piling on controls without a clear design, the environment can become brittle and confusing, which also increases risk. The goal is thoughtful design that supports the way work actually happens while still reducing exposure. That is why architecture discussions should include both security and operations perspectives, because operations knows what must be possible and security knows what must be controlled. Beginners can learn from this by remembering that secure architecture is a negotiation with reality, not a fantasy blueprint. You want to reduce risk while still enabling safe, efficient operation. Another useful way to understand these principles is to think about what they protect in OT: the integrity of control, the availability of operations, and the safety of people and equipment. Least privilege protects integrity by reducing who can change what and by limiting the reach of compromised accounts. Determinism protects availability and safety by keeping system behavior stable and making deviations visible and manageable. Defense in depth protects all three by ensuring that failure of one control does not become immediate disaster. When you map principles to outcomes, they feel less like abstract theory and more like practical decision tools. For example, if you are considering a new remote access method, least privilege asks whether access can be scoped. Determinism asks whether the method introduces unpredictable behavior or difficult to monitor changes, and defense in depth asks what other layers exist if that remote access is compromised. Those questions can be asked without deep technical detail, which is great for beginners because it means you can contribute to discussions early. Over time, you will learn the technical implementations, but the principles remain the same. The principles act like guardrails that keep decisions aligned with safety and resilience. When you step back, secure OT architecture is about making sure the environment behaves safely and predictably even when threats and failures are present. Least privilege is the discipline of reducing power to what is necessary, so compromise and mistakes have limited impact. Determinism is the commitment to predictable behavior and intentional change, which supports both operational stability and anomaly detection. Defense in depth is the recognition that no single control is perfect, so you design multiple layers to prevent, contain, detect, and recover. Together, these principles help you build environments where attackers have fewer pathways, where abnormal behavior stands out, and where incidents can be handled without panic-driven decisions that create new hazards. For a brand new learner, mastering these ideas is less about memorizing definitions and more about developing a way of thinking. You learn to ask how access is limited, how behavior stays predictable, and what happens when something fails. That way of thinking is the foundation for every other topic in OT security because it keeps you grounded in what matters most: safe, reliable operation in a world where not everything goes as planned.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.